Hello dear students, welcome back to online classes on data communication subject. So in the last two videos we have learnt about frequency division multiplexing and wavelength division multiplexing. In this video we are going to learn about time division multiplexing, and we have to solve some problems on it. So what is time division multiplexing? The other two techniques what we have learnt is they work on analog data, whereas this time division multiplexing, it is a digital process. So we will talk more about this. What is time division multiplexing? First we will study first. Time division multiplexing is a digital process which allows several connections to share the high bandwidth of a link. So instead of sharing a portion of the bandwidth as in FDM, the last technique what we have learned, here time is shared. There in FDM frequency is shared, and in wavelength division multiplexing again bandwidth is shared between different wavelength of the signals that we are sending. Here time is shared, so each connection occupies a portion of time in the link. Here in TDM we can visualize it using this figure. So this figure gives you conceptual view of TDM, that is time division multiplexing. So here each connection occupies a portion of time in the link. See here, this is connection 1, this is connection 2, or we can say them as source 1, source 2, source 3, source 4. So they have occupied different time slots in the link. Then the note here that the same link is used in FDM also. So however, the link is shown sectioned by time here, not by frequency. Okay, then in this figure portions of signals 1, 2, 3 and 4 occupy the link sequentially, as you can see. So a point to be noted here is we are concerned with only multiplexing, not switching, which means that data can come and go from any of the sources. We don't know where data goes at the end. Source 1 may be connected to source 4 and source 2 may be connected to source 3, like that. We are not discussing here where the data goes or where it come from. We are just discussing how the time slots are given and how TDM works. Okay, we also need to remember that TDM is in principle a digital multiplexing technique. Digital data from different sources are combined into one time shared link here. Okay, then however, this does not mean that sources cannot produce analog data. When sources produce analog data, we have a different process to convert that analog data into digital one that we have already learned. We will use a sampling, quantizer and encoding methods, that is a pulse code modulation method, to convert analog data into digital data that we have already learned in the last module. And after converting it into digital data, we use TDM here. Okay, then we can note that TDM is a digital multiplexing technique, and it combines several low rate channel into one high rate channel. That is the main use of this technique, TDM technique, in this bandwidth utilization section. Then we can convert, or we can divide a TDM, that is a time division multiplexing, into two different schemes. The first one we can call it as synchronized time division multiplexing, and the second one is statistical time division multiplexing. So please note these two things: synchronous and statistical TDM. Synchronous TDM, statistical TDM. So one by one we will learn them together. Then first we will learn synchronous TDM. So in synchronous TDM, each input connection has an allotment in the output, even if it is not sending data. What is the meaning of this sentence? We will discuss it with this figure. Here it is clearly visible to you. So in synchronous TDM, as I already told you, each input connection has an allotment in the output, even if it is not sending any data. So we will learn two things here: time slots and frames. You can see from the figure 6.13 what is happening here. We have three sources. First source is A, this source, second source is B, third source is C. So what we are doing here, we have converted whatever data that A has to send. This is the whole data that A has to send. This is the data that B has to send. This is the data that C has to send. What we have done here, we have cut down that data. We have cut down that data into smaller units. This is one unit, this is a second unit, and this is third unit, like that. Here in case of B, this is one unit, data unit that it wants to send. This is second data unit, this is third data unit, like that. So in synchronous TDM, the data flow of each input connection is divided into units. Okay, then where each input occupies one input time slot. So what we are doing here is we are sending these units outside using a multiplexer. How it is sent? Can you observe this part of the figure? How it is sent? We have frame 1, frame 2, and frame 3. So what this frame consists of? It consists of data units. See, observe frame 1 here. Observe frame 1. So what you can see in frame 1, we have A1, we have B1, and we have C1. Okay. Observe frame 2. What we have? We have second data unit of A, we have second data unit of B, and we have second data unit of C. Okay. Similarly, what frame 3 consists of? We have third data unit of A, third data unit of B, and third data unit of C. Okay. So what does the frame consist now? So each frame is a 3 time slots. Okay. First time slot is given for first source, second time slot is given for second time slot, source, and third one for third source. So if you have n sources here, if you have some more sources, then these frames could have had some more units, data units in each of them. That is the meaning of it. That is the meaning of it. So each input unit becomes one output unit and occupies one output time slot here. The duration of an output time slot is n times shorter than the duration of an input time slot. So here, duration of one frame, this is capital T. Okay, so if you have n sources, then duration of one output source will be T by n. Okay, that is the meaning of it. So here it is 3, we have 3 sources, so it is T by 3. Duration of one slot or one unit, that is A1, its duration is T by 3. Similarly, B1, its duration is T by 3. Similarly, C1, its duration is T by 3. Whereas the duration of frame 1 is capital T, that is 3 times this T by 3. So it should contain A1, B1, and C1. So it is 3 times T by 3, that is T, capital T. 3 into T by 3, 3 gets cancelled, and T is the answer. So if an input time slot is T seconds, the output time slot is T by n seconds. Okay. So here it is observed. If it is T, here it will occupy T by n. That is, if we have 3 sources, it is T by 3 here. Then where n is the number of connections, then in other words, a unit in the output connection has a shorter duration. It travels faster. Okay. Then figure 6.13, this figure, synchronous time division multiplexing, it is very important. It gives you the working principle of synchronous time division multiplexing. Okay. So in synchronous time division multiplexing, a round of data units from each input connection is collected into a frame. So what is shown here? So what is frame? Frame is collection of data units from every source. Okay. So it is now clearly visible. What is frame? Frame is a collection of a round of data units from each input connection. If we have n connections, a frame is divided into n time slots. Here we have 3 connections, so the frame is divided into 3 time slots, and 1 slot is allocated for each unit. So 1 for each input line here. Then if the duration of the input unit is T, the duration of each slot is T by n. Then and the duration of each frame is capital T. Okay. The data rate of the output link must be n times the data rate of the connection to guarantee the flow of data. Right. So this T and this time slot and this time slot, so we are multiplexing it. So each the data rate of this link should be greater than the combined the combined capacity of these 3 sources or units at a time. Okay. Then in synchronous time division multiplexing, the data rate of the link is n times faster and the unit duration is n times shorter. So this is the point to be noted here. This point, what is that? In synchronous time division multiplexing, data rate of link, I have told you what is link and what is channel. Link is n times faster and the unit duration is n times shorter. We'll see some examples, then you will come to know what are these things actually. So we will solve first example. Take down in figure 6.13, the data rate for each input connection is 1 kbps. That is, the data rate for each input connection is 1 kbps. We don't know how many input connections are there. Input connections means we will visualize this part. Okay, output connections means we will visualize this part from now in all the problems. Okay, so the data rate for each input connection is 1 kbps. If one bit at a time is multiplexed, that is, if you have n number of sources here, let us assume if one bit at a time is multiplexed, that is one unit here in this diagram, this unit is 1 bit in this example. That is the meaning of it. If one bit at a time is multiplexed, what is the duration of each input slot, each output slot, and each frame is the question. Okay, let us solve it. So the first one we will solve, that is part A, each input slot. What is the duration of each input slot? So to find out the duration of each input slot, the data rate of each input connection is 1 kbps. So 1 bit duration in 1 kbps can be calculated as 1 by 1000 seconds. Why 1000 seconds? Because we have 1 kbps, 1 kilobits per second is there. What is the duration of 1 bit in 1000 kilobits? That is 1 by 1000, or it is equal to 1 milliseconds. Right, 1 millisecond is the duration of in a time slot of 1 bit here. That is bit duration, in other words. So second one, B question we are answering. What was the B question? It is the duration of output slot, I think. Yes, each output slot. So what is the duration of each output slot? The duration of each output time slot is 1/3 of the input time slot. This means that the duration of the output time slot is 1 by 3 millisecond. That is, here, if three sources are there, let us assume there are 3 sources, or if there are n sources, what we can say is that the output time slot is 1/3 of the input time slot. So this means that the duration of output time slot is 1 by 3 millisecond. Then what is the third question? What is the duration of each frame? So each frame carries 3 output time slots. So what each frame carries, if there are 3 sources, consider 3 sources here for this example. So each frame carries 3 output time slot. So the duration of each frame will be 3 into 1 by 3. So similar for this diagram. So it is 3 into 1 by 3. What we are finding is, we are finding this T, capital T. So capital T is 3 into 1 by 3. That is equal to, wait a second, that is equal to 1 millisecond. So the duration of frame is the same as the duration of the input unit. So this completes example 6.5. Let us move to the next slide. Here we have one more example, 6.6, example 6.6. We will study it. So figure 6.14 shows synchronous, this figure. We will note some points. What are those? There are 4 sources, each of 1 Mbps. Okay. Then you can see frames here. How are frames? Can you observe? Frames will be having 4 data units. It is evident because there are 4 sources, data sources. So let us read out the problem. Figure 6.14 shows synchronous TDM with a data stream for each input and 1 data stream for the output. So that is 4 input sources are there and 1 output source, 1 stream, output stream is there. So the unit of data is 1 bit. So 1 unit consists of 1 bit. So a frame consists of 4 bit. That is the meaning of it. Then find A, the input bit duration, the output bit duration, the output bit rate, and the output frame rate are what we have to find out. Question is very easy. The input bit rate, first one, like the previous problem we will solve, it is 1 by 1 Mbps. 1 by 1 Mbps means it is 1 microsecond. That's it. Then the output bit duration will be 1/4 of this 1 microsecond, right? So this I think you might have understood. So when the question is asked as what is the input bit duration will be 1 by the capacity of that channel. What is the capacity of the first source? It is 1 Mbps. It can produce 1 millibits, sorry, 1 megabits per second. That is what will be the bit rate of, sorry, bit duration of one bit, that is 1 by 1 Mbps. That is it. Then coming to the next question, it was asked that here what is the bit duration in the output slot or in the output stream. In the output stream, in the input stream it will be 1 microsecond, 1 by 1 Mbps it is. So in output stream it is 1 by 1/4. Why 1/4? Because we have 4 sources. If we had 3 sources, then it is 1 by 1/3 microsecond, like that. Okay, have you understood this? I think you have understood. So first 2 questions we have answered. The output duration is 1/4 of the input bit duration, that is 1 by 4 microsecond. Why 1/4? Because we have 4 sources. If we had 3 sources, then it is 1/3, like that. Then coming to the next part, the output bit rate and the output frame rate we have to calculate. So the output bit rate is the inverse of the output bit duration. Bit rate is always inverse of the bit duration. Please keep this thing in mind. So it is, we had 1/4 microsecond as bit rate. Then what is bit duration? Sorry, what is the bit duration was 1/4 microsecond. Then what will be the bit rate? It is 1 by that amount, 1 by bit rate, that is 4 megabits per second is the capacity of that or bit rate of that output stream. Then frame rate. What is frame rate? Frame rate is always the same as the input rate. So the frame rate is 1 million frames per second, because we are sending 4 bits in each frame. Observe this figure. How many these things are coming? 1 Mbps, 1 Mbps, 1 Mbps, 1 Mbps. So the line is of 4 Mbps. Then how many frames you are sending? This line alone is sending 1 Mbps, that is 1 megabytes per second. It is sending to this stream. This line is also sending 1 megabyte. This line is also sending 1. This line is also sending 1 megabyte of this thing to the output stream. So total it is 4 Mbps, and each frame has 4 units of data, right? So 4 gets cancelled. So what is remaining? It is 10 lakh, or we call it as 1 million frames per second. That is 1 megabytes of frames, 1 mega frames per second. That is what we are getting. Have you understood? I think you have understood. If you have any doubts, please comment. Then the next question, figure example 6.7. 4 1 kbps connections are multiplexed together. 4 sources are there. 1, 2, 3, 4, A, B, C, D. Unit is 1 bit here. Okay, each of these connections are 1 kbps, 1 kbps, 1 kbps, like that. A unit is 1 bit. That is, we have a mux here. I think we have a figure for this. No, we don't have figure. So we have 4 lines, and each line is of 1 kbps, and we have a mux here. After that we have a frame here. So in each frame the data unit is one bit. That is what is the meaning of first line. Then find the duration of 1 bit before multiplexing, the transmission rate of the link, the duration of a time slot, and the duration of the frame. So can you solve this? Yeah, it is very easy. The part A, the duration of 1 bit before multiplexing is 1 by 1 kbps. That we all know, that is 1 millisecond. Like the previous problems, 2 problems. The rate of the link is 4 times the rate of the connection. That is link's data rate they are asking. So it will be 4 into, because we have 4 sources, it should be 4 times the data rate of each of the link. So it is 4 kbps. 4 into 1 kbps, 4 kbps. Then C, the duration of each time slot is 1/4 of the duration of each bit. Why 1/4? As I've already told, there are 4 sources. So 1 by 1/4 millisecond. It is also 250 microsecond. So 250 microseconds. The duration of a frame. This is the duration of each time slot, and this is the duration of frame. So each time slot ends in 250 microsecond. Then 4 into 250 microseconds, that is 1 millisecond. That is the answer for D. That is the duration of a frame. Okay, I think you have understood. I'll move to the next concept. Next concept is interleaving. So TDM can be visualized as 2 fast rotating switches. I'll show in the figure. So this is the figure for interleaving. Here what you observe is, you're observing 2 fast rotating switches. Where are they? These are the 2 fast rotating switches. Okay, visualize them. Then one of the multiplexing side, there are 2 switches, this one and this one. One will be at the multiplexing side and another will be on the demultiplexing side. Please keep these things in mind. Then we will move further. The switches are synchronized and they rotate at the same speed. Okay, these 2 are synchronized. Then they rotate at the same speed. That is the main thing to be noted here. And they rotate in different directions, opposite directions. On the multiplexing side, as the switch opens in front of a connection, that connection has the opportunity to send a unit onto the path. So this is the diagram. So whenever this switch is rotated or it is moved like anti-clockwise or clockwise, so one of the data unit will come and sit here and that will be thrown to frame. Similarly for B and similarly for C. That is the meaning. Then on the multiplexing side, as the switch opens in front of a connection, that connection has the opportunity to send a unit onto the path. Like when now it is time for A, then A's switch or A's time slot is over, then this switch rotates. Then A cannot send the data. Now B can send the data. When time slot of B is over, then C can send the data, like that. Okay, they can send the data and form a frame on the output link. Okay, then this figure, this process is called as interleaving, and this figure shows how it works. On the demultiplexing side, similarly, as the switch opens in front of a connection, that connection has the opportunity to receive a unit from the path. Okay, then this figure, interleaving process, it shows interleaving process for the connection shown in this figure 6.13, previous figure. For this, instead of at multiplexing side, we have used the rotating switches. That is the meaning of it. If we use rotating switches, we will get this diagram. Okay, then we assume that no switching is involved and the data from the first connection at the multiplexer site go to the first connection at the demultiplexer. So as we have mentioned in the previous figure, that is while studying TDM, we are not discussing about switching here. Switching represents where data goes, where the data is switched from which source to which source. Suppose A can send data to C or D at the receiving end, and B can send to some other stations at the receiving end. We are not discussing about that. We are just discussing about how the data is multiplexed and demultiplexed, and what are the different techniques, that is FDM, TDM and WDM. Okay, we are only discussing that. This is interleaving process. Then we will solve a problem on that. You will come to know some important topics in this problem. Figure example 6.8. 4 channels are multiplexed using TDM. If each channel sends 100 bytes per second, please note the units here carefully. This is bytes per second, and if we multiplex 1 byte per channel, show the frame traveling on the link, the size of the frame, the duration of the frame rate and the bit rate for the link. This is a bigger question, so we will discuss it with a figure. This is the figure that we have to discuss. So I have used colors, 4 colors for 4 different sources: blue, pink, yellow and green. The multiplexer is having 4 sources, 4 different color sources. Each frame carries 1 byte from each channel. This is frame. It carries 1 byte of information from one source. First source is blue, so 1 byte from blue, 1 byte from pink, 1 byte from yellow and 1 byte from green. So 1 byte means 8 bits, you all know. So this frame, overall frame, consists of 4 bytes or 32 bits. That is the meaning. Okay, have you understood? Okay, then each frame carries 1 byte from each channel. The size of each frame is 32 bits, that we have discovered. Then because each channel is sending 100 bytes per second and a frame carries 1 byte from each channel, the frame rate must be 100 frames per second. So this we are doing now. So 100 bytes this is sending, 100 bytes this is sending, 100 bytes this is sending, 100 bytes this is sending. So how many bytes they send in a second? They send 400 bytes in a second. Okay, so how many frames will be developed in 1 second? That is the question is asked. So in part B, I think here somewhere the size, how many frames will happen. Okay, so how many frames will be there? There will be 100 frames. That is 400 by 4. Why 4? 4 bytes for 1 frame. So there will be 100 frames. There will be 100 frames in this whole connection, right? Then frame carries 1 byte from each channel. The frame rate must be 100 frames per second. Then the duration of frame is how much? It is given in the slide. It is 1 by 100 second. It is very easy to find out. Then what is the another question part in the question they have given? The frame rate is 100 frames per second. Okay, as we all know, the frame rate is 100 frames per second. And the last question, the link is carrying 100 frames per second, and since each frame contains 32 bits, the bit rate is 100 into 32. That is 3200 bits per second, or 3200 bits per second. So each frame carries how many? 32 bits. Such 100 frames will be there. So the answer is 3200. That is the frame rate, not bit rate, frame rate. So this is it. Example 6.8, we have answered all question, I think. Then example 6.9, a multiplexer combines 400 kbps channels using a time slot of 2 bits. Read this question. This is different from our previous 3 to 4 questions. Here we have how many? 4 sources, and we have a mux. Okay, then using a time slots of 2 bits. So here we have a frame. How many slots should be there in a frame? 4 slots, because we have 4 sources, right? Then what is the another part given in the question? Using a time slot of 2 bits means in one time slot A is sending 2 bits, 0 or 1, like that. Okay, show the output with 4 arbitrary inputs. What is the frame rate, what is the frame duration, what is the bit rate, and what is the bit duration is the question given. So we'll solve one by one. I think we have a figure for this. Yeah, we have a figure for this. Whatever I have drawn in the previous slide, it is represented. We have 4 input sources. We have a mux, we have some stuff here that is going inside the mux, and each frame, what it is having 8 bits. Then that is in one time slot the sender is sending 2 bits in its time slot. Okay, we have some questions that is asked in the previous slide. We have to answer these parts. We'll answer one by one. So the first one, the link carries how many frames here? 50,000 frames per second. Why 50,000 frames per second? You observe this, you will get to know. 100 kbps, 100 kbps, 100 kbps, 100 kbps. How much it is? It is 400 kbps. So 400 kbps, 8 bits are there. So you will get 50,000 frames. Such 50,000 frames will go in one time unit. Similar like previous problem. Then next question is frame duration. Frame duration is 1 by 50,000 second, that is 20 microsecond. The frame rate is 50,000 frames per second, and each frame carries 8 bits. So the bit rate is 50,000 into 8, that is 400 kbps. This is the answer for bit rate. Then last question, the bit duration, that is 1 by 4 lakh or 4 mbps, that is 2.5 microseconds, right? The frame duration is 8 times the bit duration because we are using 8 bits here. Okay, in the previous one we did 3 into 1 by 3, but here what we have to do, here we have to multiply it by 8. Okay, that is the only difference from previous problems and this problems. Right, we will go to the next concept, empty slots. What do you mean by empty slots? Observe the figure here. We have a mux, we have some data sending from source A, we have no data sending from source B. Why this happens? We have some data that has been sent from source C, but this slot is empty. We have full data to be sent in pink or from the last source. See what happens if we have empty slots. Now this source 3 or source 2, it doesn't have any data to send. Now what it should do? Using our regular synchronous TDM, how we will frame them? This is how we frame them. First this slot will go here. Okay, for source 2 there is no data to send, so it is blank, right? Then for source 3 we have a data to send, that is yellow, this one, and this one is represented here, that is sent. Next, in one frame we had one empty slot. Then coming to the next one, this data is represented here. Then this source doesn't have any data, that is left blank, and source 3 have some data. No, it doesn't have any data, so that is also left blank, and this is sent here. So are you finding any disadvantage of this method? Whenever source doesn't have any data to send, still we allot slots for them, right? So that should not happen, isn't it? So synchronous TDM is not as efficient as it could be. If a source does not have any data to send, the corresponding slot in the output frame is empty, right? Then which is shown in this figure. Okay, in this case one of the output lines has no data to send, and one slot is another input line has discontinuous data. So that is one of the disadvantage. So how you can overcome this situation, that is what we have to learn here, right? The first output frame has 3 slots filled, the second frame has 2 slots filled, and the third frame has 3 slots filled. No frame is full. So in the next section we are going to learn about statistical TDM. In statistical TDM we will come to know uh, who has empty slots, which source has empty slots, so that we can get rid of those empty slots, and we will give more time units for those who have more data to send. So that is one of the advantage of statistical TDM that we are going to learn in the next section. Before that, we are learning a concept called as data rate management. So why this data rate management should be learned? One problem with time division multiplexing is how to handle a disparity in the input data rates. In all our discussions so far, we assume that the data rates of all input lines were the same, right? That is 1 kbps, 1 kbps, 1 kbps, 1 kbps. All the sources was 1 kbps. In another problem, we have learned that all the sources had 4 kbps or 4 mbps data rate. If we have different data rates, what will happen? Right, there are 3 strategies or combination of them can be used. What is that? That is the multi-level or multiplexing, or multiple slot allocation, and pulse stuffing. So we will learn first multi-level multiplexing. Right, what has happened here? We have multiplexed two 20 kbps lines into 40 kbps line, and we have made all the sources as 40 kbps lines. That is multiplexed to a 160 kbps line. This is called as multi-level multiplexing. Next one, multiple slot allocation. What is this multiple slot allocation? Here, this is second type. Sometimes it is more efficient to allot more than one slot in a frame to a single input line. For example, we might have an input line that has a data rate that is multiple of another input. In this figure, the input line with a 50 kbps data rate can give 2 slots in the output. We insert a demultiplexer in the line to make 2 inputs out of 1. So this is one technique, multiple slot multiplexing. Then the last one is pulse stuffing. So this is pulse stuffing. So what is that? We have a 50 kbps line, we have 50 kbps line, we have 46 kbps line. We are adding some stuff to it to make it as 50 kbps, and then we are sending it to a multiplexer which makes it a 150 kbps line. This is called as pulse stuffing. So these 3 techniques, what these 3 techniques assure us is we can manage data rate if they are uneven, if they are coming from uneven sources. Here you can see, or here you can see, all the sources have uneven data rates, right? So what we can assure from this figure, we can have equal data rates at the end using these 3 techniques. So one important question that can be asked is how data rates are managed. Explain the 3 ways in which data rates are managed in TDM. Okay, that is one of the important questions. So you have to discuss about these 3 techniques. The first one is multi-level multiplexing, multi-slot allocation, and pulse stuffing, and you have to explain these 3 techniques. So this is it. Then comes frame synchronization. Frame synchronization, we will discuss it with this diagram. The implementation of TDM is not as simple as FDM, as you all know. Then synchronization between the multiplexer and demultiplexer is a major issue here. Okay, and if the multiplexer and demultiplexer are not synchronized, what happens? A bit belonging to one channel may be received by a wrong channel. Okay, then for this reason there should be synchronization bits, right? These bits should be added at the beginning of each frame. Then these bits are called as framing bits. They follow a pattern, frame to frame, or after some frames they follow a pattern, but these framing bits should be there. Why these framing bits are needed? Because we have to get to know that whether we have correctly sent the whether we have correctly sent the frames or they are received by the correct channel or not. For this sake we need framing bits. Okay, so this is the framing synchronization pattern 101. See here, 1 is sent at the starting of the frame, 0 is sent in the, sorry, here it comes like this, sorry, 1, this 0, and this 1, 1 0 1. Okay, So using this we can synchronize, and we can get to know that whether each channel has received its data correctly or not, right? Okay, then coming to the next problem, example 6.10. Here we have 4 sources, each creating 250 characters per second. If the interleaved unit is a character and one synchronizing bit is added to each frame, find the data rate of each source, the duration of each character in the each source, then frame rate, the duration of each frame, number of units in each frame, and the data rate of the link. This is important problem. Please make a note of it. So the part A, that is the data rate of each source. I think you know the data given in this problem. That is, we have 4 sources, 1 2 3 4 4 sources we have given, each creating 250 characters per second. Means in one character we have 8 bits, such 250 characters into 4 into 8, because 4 sources are there, and 250 into 8 is bits created by these 4 sources. If the interleaved unit is a character, that is 1 byte per second, and one synchronized bit is added to each frame, means in frame we have how many units? 4 units, because we have 4 sources, and each unit has one character in it, that is 8 bit, and one synchronizing bit is added to every frame. That is what is given in the question. So we have to find the data rate of each source. What is the data rate of each source? Data rate is 250 into 8. Why 8? Because 8 bits will be there in each character, so 250 characters will be taken out. So 250 into 8 is 2000 bits per second, or 2 kbps. That is part A. Then coming to part B, what is part B? What they have asked? The duration of each character in each source. So each source send 250 characters per second. Therefore, the duration of each character will be 1 by 250 second, or 4 millisecond it will be. Coming to third part of the question. Third part of the question is the frame rate. What is the frame rate? Each frame has one character from each source. Okay, one frame has one character from each source, which means the link need to send 250 frames per second to keep the transmission rate of each source. That is, frame rate is 250 frames per second. Then the duration of each frame is 1 by 250 seconds, that is 4 milliseconds. So you can observe here, this one and this one will be same in every example, right? Then fourth one, the duration of each frame, we have answered 4 millisecond. Then eighth question, the number of bits in each frame. What is the number of bits in each frame? So each frame carries 4 characters, that is 4 characters, one from A, one from B, one from C, and one from D, and one extra synchronizing bit. So what is the number of bits here? It is 4 into 8. 4 into 8 is 32, plus one synchronizing bit, it will be 33 bits. Then the last part of the question, what is that? The data rate of the link. So the link sends 250 frames per second, as we know from the previous answers. Each frame consists of 33 bits. Okay, 32 bits plus one synchronizing bit. This means that the data rate of the link is 250 into 33. That is 8250 bits per second. Okay, that is the answer for the last part. Okay, coming to example number 6.11. I'll read out the question first. 2 channels, one with a bitrate of 100 kbps and another with the bitrate of 200 kbps. So here we have 2 channels. The first one we have 100 kbps, second one we have 200 kbps. Observe here, data rates are different, are to be multiplexed. How this can be achieved? What is the frame rate? Here we have to make use of the one of the 3 data rate management techniques that we have learned. How this can be achieved, we have to answer first. Then what is the frame rate, we have to answer. What is the frame duration, we have to answer. And what is the bit rate of the link, that we have to answer. These questions we have to answer. I think you will solve this, because we have learned 3 techniques, data rate management techniques. Tell me which one is best suited for this. tell me which one is best suited for this, and find out the answer. The solution is also given in the slides that is shared to you. Check in there, or solve it and check your answers there. Okay, then we will move to the next concept, that is digital signal service. This is very important concept. So the telephone companies, they implement TDM through a hierarchy of digital signals called digital signal service, DS service. It is also called as DS service or digital hierarchy. This hierarchy we have learnt in our FDM not FDM, yes, FDM technique video. This figure gives you digital hierarchy. So here we have DS0, DS1, DS2, DS3, DS4 lines. Okay, you can observe it. So DS0, what is the characteristic of that line? DS0 is a single digital channel of 64 kbps. Okay, so this one DS0 channel is capable to carry 64 kbps, or it is a 64 kbps line. It is usually your telephone line. Okay, one customer has 164 kbps line with the exchange, like that. So such 24 DS0 lines will make one DS1 line. That is the meaning of it. 24 DS0 lines make one DS1 line. So what is the bandwidth of DS1 line? It is 24 into 64 kbps, that is 1.44 mbps. Similarly, DS2 lines, how many DS1 lines make DS2 lines? Can you answer? Yes, it is 4 DS1 lines make DS2 lines, one DS2 line, that is its bandwidth is 6.312. Such 7 DS2 lines will make one DS3 line, then its capacity is 44.376 mbps. Then such 6 DS3 lines will make one DS4 line. So this is hierarchy. We need this. I'll give you an analogy. We have in your apartment, we have different customers. Suppose we have 24 customers in your apartment. Each one will be having DS0 line. Those DS0 lines will be clubbed into one DS1 line, and that is connected to exchange, like that it is. Okay, and this hierarchy follows like this. Okay, that is one of the analogy we can have. Then what are T lines? You have T lines and something called as E lines here. These are two standards. Okay, T lines are followed in E lines are followed in European countries, and T lines are followed in the other part of the world. T lines are digital signals or digital lines designed for the transmission of digital data, audio or video. They also can be used for analog transmission, provided the analog signals are first sampled and then time division multiplexed. So here is the hierarchy of DS and T line rates. So DS1 is equivalent to T1, which is equal to 1.544. It has 24 voice channels. Then DS2 is equal to T2, 96 voice channels. DS3, T3, 672. DS4, T4, 4032 lines will be there, voice channel lines. Coming to E lines, this is followed in European nations, or it is European standard. E1, it has 048, then it has 30 voice channels, like that the hierarchy goes. E2, 8.448 mbps, then voice channels, 120 voice channels will be there. E3, 480 voice channels. E4, 1920 voice channels will be there. Okay, that is the meaning of it, E lines and T lines. Then this is one of the T1 line for multiplexing telephone lines. So it is 24 voice channels are there. We have pulse code modulation, and we have a time division multiplexing. So we have converted 24 lines and we have made a T1 line, 1.44 mbps line. This is how multiplexing is achieved in telephone exchanges. This is a frame structure that is not so important for you. Then comes the next concept, statistical time division multiplexing. So as we have found out one of the inefficient part of TDM, that is when we have empty slots in one of the sources, then TDM becomes, that is synchronous TDM becomes inefficient. So we have come up with an idea called as STDM, that is Statistical Time Division Multiplexing. As we saw in the previous section in Synchronous Time Division Multiplexing, each input has a reserved slot in the output frame there. This can be inefficient if some input lines have no data to send. In Statistical Time Division Multiplexing, slots are dynamically allocated. That is one of the added advantage here. That is, slots are dynamically allocated to improve bandwidth efficiency. Only when an input line has a slot's worth of data to send, it is given a chance. Then in statistical multiplexing, the number of slots in each frame is less than the number of input lines. So for this, we have this figure. We have differentiated the two techniques here. The first one is synchronous TDM. We have some blank slots in A and C and as well as in E. Using the same figure, we have drawn STDM. So here we need to send some empty slots. Here we are not sending any empty slots, because whenever a line is needed, it has some data, then we will allocate this thing to it. See here, frame A here, frame 1 here, A1 has sent the data, B1 has sent the data, D1 has sent the data. And we have some other things here that we didn't had here. We had synchronizing frames here or framing bits here, but we have addresses here, A, B and D. So whenever only the required lines are sending data, they also need to send addresses. Who has sent? A has sent A1, B has sent B1, D has sent D1. Similarly here in the second frame, or in the second time slot, who has the data to send? B2 has the data to send, D2 has the data to send, and E2 has the data to send. So B2 has sent the data. I'll clear a second. B2 has sent the data, D2 has sent the data, and E2 has sent the data, and they have also sent their addresses. B has sent B2, D has sent D2, E has sent E2. That is the meaning of this figure. So this is how statistical TDM works. Okay, I think you have understood. Then one thing we have to keep in mind is in STDM, that is in statistical TDM, we need to have addresses so that we can demultiplex correctly and send the required bits to the required lines at the other end, right? So about bandwidth, in statistical time division multiplexing, the capacity of the link is normally less than the sum of the capacities of the channel. The designers of statistical TDM define the capacity of the link based on the statistics of the load for each channel. So if on average only X% of the input slots are filled, the capacity of the link reflects this. So during peak times, some slots need to wait. This is one of the disadvantage of statistical TDM, but it doesn't happen all the times. Okay, so we need we need addressing here, and we don't need synchronization bit, as we have discussed here. As we needed here, 0 was the synchronization bit, 1 was the synchronization bit. Since we are using addressing bits here, we don't require synchronization bits here. Okay, that is one of the added advantage in statistical time division multiplexing. So this is all about time division multiplexing. In the next video, we will cover spread spectrum, the last part in bandwidth utilization. So as you all know, bandwidth utilization, efficiency of a channel can be implemented into two categories. That is, the first one is multiplexing categories and the second one is spread spectrum categories. So first category we have already learnt. In first category we have learnt about frequency division multiplexing, wavelength division multiplexing and TDM. In TDM we have learnt two schemes, that is statistical and synchronous. In WDM we have learnt that there are two techniques, that is coarse and dense WDM. Okay, so in the next video we are going to cover spread spectrum. Till then, take care. Thank you.